Our universe, in its vastness and complexity, is governed by two seemingly disparate sets of rules. These rules dictate the behavior of everything from the smallest particles to the largest structures in the cosmos. On one hand, we have Einstein's theory of relativity, a cornerstone of modern physics, which elegantly describes gravity and the large-scale structure of the universe. It paints a picture of a smooth, continuous space-time, where galaxies dance in a cosmic ballet. On the other hand, there's quantum mechanics, a theory that governs the microscopic world of atoms and particles. Here, things are fuzzy, uncertain, and governed by probabilities rather than certainties. For decades, scientists have puzzled over a fundamental question: how the solid, predictable world we experience every day, with its seemingly definite properties and clear-cut rules, could possibly emerge from the strange, probabilistic quantum realm, where particles can be in multiple places at once and the act of observation changes everything. Enter Quantum Darwinism, a groundbreaking theory proposed by Wojciech Zurek in 2003, seeking to resolve this very paradox. It offers a compelling explanation of how the quantum world transitions into the classical world we perceive, bridging these seemingly incompatible worlds. The core idea borrows inspiration from Charles Darwin's theory of evolution, suggesting that the environment, in its entirety, acts as a passive observer, constantly monitoring and interacting with the quantum realm. This environment is not merely a backdrop, but an active participant, constantly interacting with quantum systems, probing their states and influencing their evolution. Within this constant interaction, only the most stable quantum states, those that can withstand the relentless probing of the environment, are able to survive these interactions, much like the survival of the fittest in the natural world. These robust states then imprint their information throughout the environment, leaving multiple copies of themselves in the surrounding world. These fittest states, the ones that have successfully propagated their information, become the objective, classical facts that we all agree on, the shared reality that forms the basis of our everyday experiences. Consider something as simple as the position of a football or the temperature of a cup of tea. Quantum Darwinism reframes our understanding of reality, suggesting that it's not a fundamental property of the universe, but rather an emergent phenomenon arising from the underlying quantum interactions, not a fundamental one. The classical world, with all its apparent solidity and certainty, is ultimately the result of a relentless quantum competition, a constant struggle for survival among quantum states. In this competition, only the most robust states, those best suited to withstand environmental interactions, persist and propagate. Our shared reality, the world we all experience and agree upon, is therefore a product of this cosmic selection, a process that continuously transforms quantum possibilities into the classical certainties that define our everyday lives. This perspective invites us to fundamentally rethink how we see the familiar world around us, suggesting that what we perceive is merely the visible tip of a vast and hidden quantum drama, a world of possibilities constantly vying for reality. At the heart of quantum mechanics lies one of its most profound and enduring mysteries, the measurement problem. It's a question that has puzzled physicists and philosophers alike for nearly a century. At its core, the measurement problem asks, why do we consistently observe definite, single outcomes in our experiments, when quantum theory fundamentally predicts that systems exist in a superposition of multiple states simultaneously? Consider a particle, or even something more macroscopic, like Schrödinger's cat, existing in a probabilistic blend of all possible states until the moment it is measured or observed. It's a bizarre concept, challenging our everyday intuitions. The act of measurement seems to instantaneously force a collapse, abruptly transitioning from a multitude of coexisting possibilities to a single concrete reality that we can perceive and record. The traditional Copenhagen interpretation offers a simple, albeit unsatisfying answer. Measurement causes collapse, but it deliberately avoids delving into the underlying mechanisms, never explaining precisely how or why this collapse occurs. This inherent ambiguity creates a puzzling divide. Quantum systems, governed by the Schrödinger equation, evolve smoothly and predictably in a continuous wave function until they are observed, at which point they instantaneously jump to a single definite outcome. But what exactly counts as a measurement in this context? Is the presence of a conscious observer fundamentally required to trigger this collapse? Or can any interaction with a measuring device suffice? And furthermore, if everything in the universe is ultimately governed by the laws of quantum mechanics, why does one particular part of the system, the so-called observer, possess the seemingly special power to force the rest of the system to collapse into a single state. The measurement problem starkly exposes a fundamental conflict between the continuous, deterministic evolution of quantum systems, as described by the Schrödinger equation, and the seemingly random, definite outcomes that we consistently experience in our macroscopic world. It's a profound puzzle that has sparked countless debates, fueled numerous interpretations of quantum mechanics, and continues to challenge our understanding of reality itself. Among the various proposed solutions, quantum Darwinism offers a particularly promising and physically grounded explanation, fundamentally shifting the focus away from the role of observers and instead emphasizing the crucial role of the surrounding environment. It posits that the environment, rather than consciousness or a specific measurement apparatus, plays the key role in selecting and amplifying certain quantum states, ultimately leading to the emergence of what we perceive as classical reality. Quantum Darwinism offers a compelling perspective, tackling the perplexing measurement problem that has puzzled physicists for decades. It provides a framework for understanding how definite outcomes arise from the probabilistic nature of quantum mechanics. It does so by fundamentally rethinking the environment's crucial role in shaping what we perceive as reality. In the standard textbook view, a quantum system is often treated as isolated. However, in reality, no quantum system is ever truly isolated. It's always relentlessly interacting with its surroundings, exchanging energy and information with countless other particles. This constant interaction, a process known as decoherence, fundamentally alters the quantum system, causing quantum systems to lose their delicate superpositions and transition into more classical-like states. To illustrate this, imagine a secret whispered in a room absolutely full of microphones. The environment, acting like these microphones, listens in, constantly recording information about the system's state, its properties, and its interactions. Decoherence, in essence, unravels quantum coherence, the very fabric that allows for quantum weirdness, forcing the system into a more predictable and stable state, one that aligns better with our everyday experiences. But quantum Darwinism takes this idea a step further, arguing that the environment doesn't just passively destroy quantum information, but actively and selectively preserves and broadcasts certain pieces of that information far and wide. This broadcasting favors only specific, robust pointer states, which are the only ones that can effectively survive this environmental scrutiny and replication process. In this sense, the environment acts as a natural filter, relentlessly weeding out fragile quantum possibilities that are not robust enough to leave an imprint on the world. Therefore, there's no magical collapse of the wave function, but rather a gradual physical process akin to natural selection, favoring certain states over others. The environment, in effect, measures the system and makes a selection long before any human observer even arrives on the scene. It selects, environment selects, the pointer states, effectively choosing the fittest survivors, those whose information is redundantly imprinted and widely distributed everywhere throughout the environment. Ultimately, our objective reality is built from these stable survivors, the robust building blocks that have proven their resilience. Therefore, the measurement problem, in this light, dissolves into a compelling story of environmental selection, relentless filtering, and the power of information redundancy to shape our perceived reality. Pointer states are the stable quantum states that survive environmental scrutiny. While a quantum system can exist in countless superpositions, pointer states behave predictably when bombarded by the environment. For example, a dust mote's position is constantly recorded by scattered photons, making its location a pointer state. If the mote were in two places at once, the superposition would be destroyed instantly by environmental interaction. Pointer states are the classical states hiding within the quantum world, robust, stable, and able to imprint their information without being disturbed. They are the building blocks of our classical reality, naturally selected by the environment. When we observe the world, we're accessing information about pointer states already stabilized by the environment. The definite properties we see are the survivors of a relentless environmental audition. Our reality is built from these triumphant quantum states. Quantum Darwinism explains why we all agree on what we see. Objectivity arises from the environment's role as a witness. When the environment interacts with a quantum system, it creates countless redundant copies of information about the pointer state. Billions of photons, for example, each carry away the same record of a dust mote's position. This redundancy means any observer can sample a tiny fraction of the environment and get the same answer. The information is public, not private, encoded everywhere, available to all. Objectivity emerges because the environment creates an overwhelming consensus. Observers are just latecomers, intercepting messages already broadcast by the environment. The measurement has already happened, we're just reading the news. This demystifies measurement and grounds objective reality in physical information redundancy. The Darwinism in Quantum Darwinism is more than a metaphor. It's a deep analogy. In biology, traits are passed on, variation exists, and selection favors the fittest. In the quantum world, pointer states reproduce by imprinting their information onto many fragments of the environment. Variation comes from quantum superposition, the system's many possible states. The environment acts as the selective pressure, testing which states are robust. Only the fittest, pointer states, survive and have their information copied. Fragile superpositions are quickly destroyed, evolutionary dead ends. Just as natural selection favors well-adapted organisms, Ein selection favors states that withstand environmental scrutiny. The classical world is the result of this relentless quantum selection. Our reality is the product of a cosmic struggle for existence, where only the most stable quantum states persist. This analogy makes the abstract world of quantum physics more intuitive. It connects the emergence of classical reality to a universal principle: survival of the fittest. A theory is only as strong as its evidence, and quantum Darwinism has begun to pass experimental tests. In 2010, researchers used quantum dots, tiny artificial atoms, to observe how the environment selects and records information. They found that information about stable pointer states, like spin-up or spin-down, was copied multiple times into the surrounding photons. For every direct measurement, the environment held about 8 redundant copies. This confirmed the theory's prediction. The environment actively broadcasts information about classical properties. These experiments move quantum Darwinism from speculation to testable physics. While not definitive proof, they provide strong evidence for the theory's central mechanism. The emergence of our shared reality is a physical process we can observe and measure. No theory is without debate, and quantum Darwinism faces its share of criticism. Some argue the division between system, environment, and observer is arbitrary. How do we justify these splits in a universe that's fundamentally quantum? Others point out that while decoherence explains why we don't see superpositions, it doesn't explain why we see one specific outcome. Some critics say quantum Darwinism is just a new narrative for well-known physics, not a fundamentally new theory. Proponents respond by refining the theory and engaging with these challenges. This ongoing debate is a sign of a healthy, evolving field. The search for a complete understanding of quantum reality continues. Quantum Darwinism is more than a technical fix, it's a profound shift in how we see reality. It removes the observer from the center, making reality objective because the universe is already watching itself. The theory is crucial for quantum technologies, helping engineers protect fragile quantum bits from environmental scrutiny. It unifies the microscopic and macroscopic worlds through a principle we know from biology: natural selection. The classical world is not a static backdrop, but an ongoing product of quantum evolution. Reality is layered beneath our stable world lies a sea of quantum possibilities. Our world is the stable crust, selected by the environment's relentless gaze. Quantum Darwinism brings us closer to answering what is reality. The quest continues, fueled by ideas as elegant as this one.